Hello students, in our last class, in our previous classes, what we have discussed about the Coulomb's law, about electric field intensity and electrostatic force, and we have solved few problems on that, and we have derived the mathematical equations for all those things by considering line charge, point charge, surface charge and volume charge, and we have derived the equations for all the considerations. The last part of this particular module is electric flux and electric flux density, right? These are the two topics we need to discuss, and we need to solve few problems on this particular topic. So what do you mean by electric flux? So according to the Faraday's experimental observations, electric flux lines are visualized as electric field intensity, which in turn electric field intensity can be visualized as electric flux lines. Suppose if I consider a point charge here, so it will induce electric field intensity around it. So Faraday observed that this electric field intensity is visualized as electric flux lines. This is what we need to study in this particular session. Okay, the agenda of this particular session is electric flux, lines, electric flux density and problems on this. Okay, this is the agenda of this particular session. Now according to the Faraday's experimental observation, as I said now, electric field intensity is visualized as electric flux lines, right? Electric field intensity E is visualized as electric flux lines. How, on what basis electric field intensity is visualized as electric flux lines? There should be some conditions, right? So in order to visualize electric field intensity in terms of electric flux lines, there should be four conditions. The first condition to be satisfied is, the electric flux lines originates from positive charge and terminates at negative charge. That is the first condition. Electric flux lines originates at positive charge and terminates at negative charge. This is the first condition to be satisfied. What is the second condition? The direction of electric flux lines is equivalent to the direction of electric field intensity. Okay, direction of electric flux lines are equivalent to the direction of field E. Direction of field E. So what is the direction of electric field? So the direction of electric field is from positive charge to negative charge. So the direction of electric field E is from positive charge towards the negative charge. Therefore, the direction of electric flux lines also from positive charge to negative charge. This is the second condition. Then coming to the third condition, see, the third condition is when the charge with Q coulomb, when the charge of magnitude of Q coulomb is equivalent to the q number of flux lines. The charge with magnitude q gives the q number of flux lines. Flux lines. This is due to the SI unit. A charge with magnitude of q coulomb produces the q number of flux lines. This is the third condition. Then coming to the fourth condition, so whenever the electric field intensity is more, wherever the electric field intensity is more in a particular region, then more crowded will be the electric flux lines. Got it? So wherever the electric field intensity is more, in that region electric flux lines are crowded. That means the electric field intensity and flux lines are proportional, directly proportional. Wherever the weak electric field intensity is there, in that case the electric flux lines are less. Okay, wherever the electric field intensity, strength of the electric field intensity is more, the crowded will be the electric flux lines. Got it? That is the fourth condition. Where the electric field strength is more in a particular, in a region, then electric flux lines are crowded in the same region. So it is understood that when the electric field strength is more, the electric flux lines are more. When the strength is less, the number of flux lines are less. Therefore, electric field intensity and the number of lines are directly proportional. By this point, we can understood that electric field intensity and flux lines are directly proportional. According to SI unit, when the charge with magnitude q coulomb produces the q number of flux lines. Got it? This is the next part. So the direction of electric flux lines is equivalent to the direction of electric field intensity. So electric flux lines originates from positive charge and terminates at negative charge. When the electric flux lines obeys all these 4 points, then electric field intensity can be visualized as electric flux lines. Okay? So if all the 4 conditions satisfies, then electric field intensity E can be visualized as electric flux lines. This is what Faraday proposes. Okay? So now coming to the symbol for this electric flux lines. Coming to the symbol for this. What is that symbol? So the Greek letter psi. Psi has been used. Symbol for electric flux. A Greek letter psi has been used as a symbol for electric flux. So according to this point, psi can be approximated to q. Why? Because the electric flux is equivalent to the magnitude of charge, because there are q number of flux lines present when the charge is having the magnitude of q. Therefore, psi can be replaced by q. Got it? So a charge with magnitude q coulomb is equivalent to the electric flux lines, that is psi. Psi is the symbol used. Got it? This is about electric flux lines. So in order to say the electric field intensity to be viewed as a electric flux lines, these 4 conditions, 4 rules to be satisfied. So electric flux symbolically represented as psi, which is equivalent to the charge of magnitude q because of this condition number 3. Okay? Continue with the next topic, that is electric flux density. symbol is D. Electric flux density, the symbol which we have used is D. What do you mean by electric flux density? So we know what is electric flux now. So electric flux is equivalent to the electric field intensity when those four conditions get satisfied. Now what do you mean by flux density, electric flux density? The symbol is different, D. Now electric flux density D is a vector which represents the surface density of electric flux lines. I will repeat, electric flux density D is a vector which represents the surface density of electric flux lines. The direction of this electric flux density is equivalent to the direction of electric flux lines, which in turn we can call it as direction of electric flux density is equivalent to the direction of electric field intensity, because electric flux lines is in the same direction with respect to electric field intensity. Therefore, we can say electric flux density is also in the same direction of electric field intensity. Then, what is the magnitude of this electric flux density? The magnitude of electric flux density is proportional to the number of electric flux lines, which passes through the unit surface area. That surface is kept normal to the direction of electric flux lines. I will repeat, listen carefully. The magnitude of this electric flux density is equivalent to the number of flux lines passed through the unit surface area when the surface is kept normal to the direction of electric flux lines. That is called electric flux density, magnitude of electric flux density. So let me write this. Electric flux density D is a vector which represents surface density of flux lines. Okay, this is the first point. Its direction is equivalent to the direction of flux lines. In other words, equivalent to the direction of electric field intensity. Got it? Then its magnitude is proportional to the number of flux lines passes through unit surface area when the surface is kept normal to the direction of electric flux lines, and it is defined as D is equal to D proportional to the number of flux lines. Number of flux lines is represented by symbol psi, which passes through the unit surface area. The number of flux lines per unit surface area. The surface area is represented by symbol S. So this is the definition of electric flux density D is equal to psi divided by S. The number of flux lines per unit surface when the surface is kept normal to the direction of flux lines. See, this is the surface S, which is kept normal to the direction of flux lines. This is the direction of flux lines. Got it? So when this condition happen, this equation holds good. Suppose there is one more condition. So we have a surface. Let us consider a surface where the number of flux lines are infinite numbers. Okay, continuous distribution of charges case you consider. Okay, under that circumstance, the continuous distribution of charges leads to the change in electric flux density at every point in that particular surface. We know that in a surface consists of many number of charges, infinite number of charges. Okay, each of the charge will contribute to the density, electric flux density. Okay, so as I said earlier, in particular region, when the electric field intensity strength is strong, the surface density value is strong. When the electric field intensity strength is less, then the electric flux lines are less, the number of electric flux lines are less. So due to these variations, electric field intensity, electric flux density D also varies. Under that circumstance, let us consider a elementary flux lines per elementary surface area. Elementary flux lines per elementary surface area. So it will give D. Okay. As I said in our previous classes, we have set a limit saying that as delta S, the surface area tends to 0, as the surface area, the length, elementary volume, elementary area tends to 0, this gradient operator changes to differential operator, right? Therefore, D is equivalent to limit of delta S tends to 0, delta psi divided by delta S is equivalent to d psi divided by ds. D psi divided by ds. As delta S tends to 0, the gradient operator changes to differential operator, d psi divided by ds. Therefore, D can be written as d psi divided by ds. Under what circumstance? When the continuous variations may happen, then the flux density is given by this equation. Got it? So another condition we need to consider here. So as I said earlier, the surface needs to be kept normal to the direction of this flux lines, right? So under that circumstance, this equation holds good. What happens when the surface is not kept perpendicular to the flux lines? See, in this particular case, this is the direction of flux line. The surface is not kept perpendicular, so which is at the angle theta, which is not equal to 90 degree. So under this circumstance, what will happen? So under this case, the flux density is obtained by using dot product. The delta psi means electric flux lines is obtained by using dot product between these two quantities. What do you mean by dot product? See, let me recall the previous case. Dot product between two vectors is given by dot product between vector A and B is given by the magnitude of A into magnitude of B into cos theta. This is the equation for dot product between A and B. Okay, where A and B are magnitude of these two vectors. Theta is the angle between A and B, angle between A and B quantities, where theta is the angle between A and B. In this case also, we need to consider the dot product. See, the surface area, this is delta S, this is the surface we are considering. We are considering the elementary surface, that is ds. ds is the elementary surface we are considering. This is the direction of the flux line. So which is inclined at an angle theta. So in order to obtain the maximum electric flux density, it should be normal. But here in this case, which is kept at an angle theta. Under this circumstance, the electric flux density is obtained by using dot product between these two quantities. Got it? This could be obtained by using dot product. Dot product is equivalent to the dot product between any two vector is equal to the magnitude of those two vector into cos theta, where theta is the angle between these two quantities. Let me write the geometrical representation of the consideration which we have taken now. Now what is this? This is the elementary surface ds. Okay. Now this is the direction of d, vector d. Okay. Now there is a normal vector, that is n cap, erect perpendicular from this surface. So this is the angle theta between this and d. Okay. In order to obtain electric flux lines d psi from this particular case, out of this particular surface area ds, we need to take the dot product between these two quantities. We need to take the dot product between these two quantities. That is, see here, if I cross multiply this, what will happen? D psi is equal to d dot ds. See, if we cross multiply this quantity, d psi is equal to dot product of vector d and ds. Okay, the dot product between these two quantities gives the number of flux lines at the elementary surface area ds, where ds, the vector ds is equal to n cap into ds, where vector ds is equal to n cap into ds. This vector is in the direction of n cap. What is n cap? N cap is the perpendicular line drawn from the surface in order to have the inclination theta with respect to orientation of this flux line. Okay, that is why we are getting the dot product. See, so the flux line out of this elementary surface area ds is d psi, which is obtained by getting the dot product between this quantity and the vector ds. This vector ds is obtained by using the area ds and the unit vector n cap. Got it? So ds is the vector obtained by multiplying n cap with ds. So this is the equation which gives the electric flux lines under the case when the electric flux lines are not normal to the surface, which is inclined at an angle theta. Got it? Now coming to the next topic, what is the relationship between D and E? What is D? Just now we have discussed about D, that is electric flux density. What is E? Electric field intensity in our previous classes. Now relationship between E, electric field intensity, and D, electric flux density. What is the relationship between these two quantities? Now let me write the mathematical expression for this one. So we know that D is given by psi divided by S. Okay, what is D? Electric flux density. What is psi? The number of electric flux lines passes through the unit surface area. Okay, so in order to derive the relationship between E and D, let us have an experimental setup. Let us assume a charge Q. Let us assume a point charge which is having a magnitude of Q. So which creates a electric field intensity around it. So assume this as a sphere. Assume this as a sphere. Okay. So then axis in a rectangular coordinate system, we can write like this. This is Z, this is Y, and this is X. Okay. Assume this as a sphere of radius R. Assume the sphere of radius R. This is the point which is kept at origin which is having the magnitude q coulomb. So electric flux lines are perpendicular to the surface. Electric flux lines are perpendicular to the surface. As I said earlier, these electric flux lines should be perpendicular to the surface. Since the sphere we are considering, these lines are perpendicular to this sphere. Now, according to this equation, D is equivalent to Q divided by S, because we knew that psi is equivalent to Q according to the condition number 3 in the previous discussion, right? When the charge is having a magnitude of Q, that means Q number of flux lines will be observed. Therefore, psi is equivalent to Q. Therefore, D is given by Q divided by S. What is S? S is the surface area. What is the surface area of sphere? 4 pi r square. 4 pi r square is the surface area of sphere. Therefore, D is given by Q divided by 4 pi r square. Now, D is a vector. We know that D is a vector which represents the surface density of electric flux lines. Then, we can introduce a unit vector in order to represent electric flux density in terms of a vector. Then, D is given by, in terms of vector form, Q divided by 4 pi r square into A cap r. So, consider this as expression 1. Now, write the expression for E. What is E? Electric field intensity. Expression for E is Q divided by 4 pi epsilon naught into r square into A cap r. Consider this as expression number 2. Compare equation 1 and 2. So what you are going to get? See, E is equal to Q divided by 4 pi r square into A cap r. Take this epsilon naught to the numerator. What is this quantity? This quantity is equivalent to the vector D. Therefore, D is equal to epsilon naught into E. This is the relationship between electric field intensity and electric flux density. Got it? So, electric flux density D is equal to epsilon naught into electric field intensity. Suppose when volume charge has been considered, what will happen to this equation? When volume charge distribution has been considered, what will happen to this equation? We know that volume charge distribution, the equation for E is equal to integration volume integral of rho v into dv divided by 4 pi epsilon naught r square into A cap r. This is the equation which we have derived, right? So for volume charge distribution. Now, see, E into epsilon naught is equal to integration from rho v into dv divided by, what happened? 4 pi r square into A cap r. What we are going to get now? So this is the expression for D, electric flux density. See, epsilon naught into E is given by electric flux density. Therefore, D is equal to integration rho v into dv divided by 4 pi r square into A cap r. This is the equation for volume charge distribution. Got it? Thank you. Let us solve a problem on electric flux density. Okay. So let me read the problem statement. A point charge Q of 30 nanocoulomb is located at the origin in Cartesian coordinates. Find the electric flux density and electric field intensity at point 1, 3, minus 4 meter. Okay. This is the problem statement given. So let us solve this problem. So what are the things we need to identify? D, electric flux density to be calculated, electric field intensity E to be calculated. Now let us write this problem statement in a pictorial representation. We need to calculate the electric field intensity at point P which is located at 1, 3, -4 meter in a Cartesian coordinate system. The charge is kept at origin 0, 0, 0. A point charge is located at origin, therefore its coordinate is 0, 0, 0. The distance between this origin and this point P is r. The vector, unit vector, is acting along this direction, acting along in this direction. Okay. Now we need to calculate the unit vector a cap r. We know that unit vector a cap r is equal to vector divided by its magnitude, right? So how to calculate r? By using distance formula. So we know that the thumb rule, tip minus tail. So 1 minus 0 into a cap x plus 3 minus 0 into a cap y plus minus 4 minus 0 into a cap z divided by square root of 1 square plus 3 square plus minus 4 square. Got it? Now what we are going to get? A cap r is equal to a cap x plus 3a cap y minus 4a cap z divided by root 26. What is the first quantity we need to calculate? E. By using E we can calculate D, because we know that D is equivalent to epsilon naught into E. Therefore you calculate E first, electric field intensity first, then deduce the electric field intensity equation to electric flux density D. Okay, let us calculate E. E is equal to Q divided by 4 pi epsilon naught into r square into a cap r. This is the equation we knew. We have solved many number of problems on this. Therefore E is equal to, what is the value of Q? 30 nanocoulomb, 30 into 10 power minus 9 divided by 4 pi into epsilon naught, 8.854 into 10 power minus 12 into r square. What is the value of r square? We know that r is equal to root 26, r square is equal to just 26. Okay, r square is 26 into a cap r. What is the value of a cap r? Ax, a cap x plus 3 a cap y minus 4 a cap z divided by root 26. If we try to solve this equation, what we are going to get is E is equal to 10.375 into a cap x plus 3 a cap y minus 4 a cap z divided by root 26. If we solve this equation further, then E becomes 2.034 into a cap x plus 3 a cap y minus 4 a cap z volt per meter. This is the expression for E. Okay. Now magnitude of E. Magnitude of E is given by E divided by a cap r. Magnitude of E is equal to E divided by a cap r. What is E? E is 2.034 into a cap x plus 3 a cap y minus 4 a cap z divided by, what is a cap r? A cap r is a cap x plus 3 a cap y minus 4 a cap z divided by root 26. These two quantities gets cancelled. The magnitude of E is equal to 2.034 into root 26, which is again equivalent to 10.375 volt per meter. This is the magnitude of electric field intensity. What is the second quantity we need to calculate? this is the first quantity we have calculated. What is the second one? D is equal to epsilon naught into E. That is given by 8.854 into 10 power minus 12 into E. What is the expression for E? 2.034 into a cap x plus 3a cap y minus 4a cap z. This is the expression. Now we need to solve. D is equal to how much? 1.8 into 10 power minus 11 times of a cap x plus 3a cap y minus 4a cap z. Okay, this is the expression we have got. If we try to solve it for its magnitude, magnitude of D is equal to du divided by a cap r. What is D? 1.8 into 10 power minus 11 into a cap x plus 3a cap y minus 4a cap z whole divided by a cap r. What is a cap r? This quantity. A cap x plus 3a cap y minus 4a cap z divided by root 26. These two quantities get cancelled. This root 26 goes to numerator. Then magnitude of this is 1.8 into 10 power minus 11 into root 26. What is the value we are going to get? D is equal to 9.8 into 10 power minus 11 coulomb per meter square is the unit of D. Coulomb per meter square. This is the magnitude of D and this is the magnitude of E. 10.375 volt per meter is the magnitude of electric field intensity. 9.8 into 10 power minus 11 coulomb per meter square is the magnitude of electric flux density. Got it? So this is how you need to solve the problem on electric flux density. Understood? Okay. Thank you.